So here's another phase portrait. Very similar to the one that we were looking at on Friday, where we've got vectors coming in on one line and going out on another. So this is very similar to the saddle point we were talking about on Friday. But if both of my eigenvalues are positive, then everything should be going out, in which case we get an image that looks more like this one. And again, we see the two different eigenvectors. The line -2, 1, and the line 1, 1. And we see the dispersal out along both of them. We call the origin a source if everything is going out. If both of my eigenvalues were negative, everything be coming in. We call it a sink. So geometrically, phase portraits change depending on the signs of the eigenvalues involved. But those were still all three options, sources, sinks, and saddles, were for two non-repeated, two distinct eigenvalues. So what happens if they're not distinct? Well, then it depends on the vectors. Here's a linear system. But it's 3 by 3 this time. I did that on purpose. Because when I do work out my eigenvalues, with a little bit of work, I get one of the eigenvalues twice. When you work out the determinant over here, you're going to see something with a lambda cubed in it. Just graph that rather than try and solve it analytically. And you can tell me what the x-intercepts are. The x-intercepts are 1 and 2. I would like you to work out what happens when lambda is 1. And give me some eigenvector results here. If I put in lambda equals 1, what is the reduced row echelon form I get from this? 3 cheers for the algorithm on the graphing calculator.
Zero. Well, I guess it's all zeros in the last column. That's 1, 0, -1, and then 0, 1, -1. The last row is all zeros.
Okay, give me equations. What equations go with those non-zero rows in our matrix?
X1 equals X3, then X2 also equals X3.
So a vector that works is just going to depend on what I pick for x3, right? So if I let x3 be 1, then I would get 1, 1, 1. There's the eigenvector that goes with 1. I like it. But what happens when lambda equals 2? As soon as I put in the value 2, I notice all 3 rows are exactly the same. So that's really just one equation. And if I do the reduced row echelon form, I'm not just going to get 1 row of zeros, I'm going to get 2 rows of zeros. But that means there's only one equation. And that equation is x1 minus x2 minus x3 equals 0. Or if I rearrange it as you did, Hayden, in the first one, I get x1 equals x2 plus x3. A reminder of terminology from algebra and or linear algebra. The variables over here on this side are called free variables. Variables on this side are called bound variables. So I have 2 free variables here. Only had 1 up there. I had 1 choice. But here I have 2 choices. I can choose x2 or x3, which really means I don't have 1 vector. I have 2. I can think of this as letting any vector be for x2 and any vector be for any number be for x2, any number be for x3. So I could think of this as an x2 part with that vector and an x3 part. Oops, I wrote those backwards. An x2 part with this vector and an x3 part with this vector. Oh. 2 vectors, 1 value, 1 vector, 1 value. So when I start putting this together, because I have 3 vectors, this is sufficient. I can still do exactly what I want before. I can say that x of t is 1, 1, 1 e to the 1t. That gets a c1. c2, 1, 1, 0 e to the 2t. And c3, 1, 0, 1 e to the 2t. As long as I have enough vectors, I'm fine. Those vectors point in different directions. Works perfectly.
Like that, like each eigenvalue, like that.
No, and that's the part that sucks. Crap. Ah. Congratulations, you've read the next sentence off of my notes. Ah, crap, this doesn't always work like that. It would be so nice. Oh, would be amazing. But no, sometimes my set of vectors is deficient. If I don't have enough vectors, I need another one. I'll do a 2x2 case. So I want to take the determinant. AD minus BC, -1 minus lambda, times 5 minus lambda minus 3 times -3. So let's see. This is -5 minus 5 plus 1 is -4 lambda. Plus lambda squared minus becomes plus -9. I get lambda squared minus 4 lambda plus 4, which is the same as lambda minus 2 squared. So the only eigenvalue I have is 2. Find me a corresponding eigenvector. Hayden, if I got 2, I'd be brilliant. But this time I only get 1. If I put 2 in up here, -3, 3, -3, 3, 0, 0. Oh, crap. The only thing I get is x1 minus x2 equals 0, or x1 equals x2. Damn it. So my first reaction is I should use 1, 1, e to the 2t. I like that. That would be wonderful. But I need another piece. This is only one direction. I don't have a linearly independent set of solutions. I don't have a fundamental set. I need 2 solutions to have a fundamental set. It's 2 by 2. Got to end up with 2 solutions. Okay, wait a minute. What did we do last time when we had a repeated root? Or in this case, I put a t, right? Let's suppose I did that. Well, I want to check and see if these are independent from one another, right? If these are independent, then I'll be good. But for these to be independent, what do I need to check? There's a name for the thing I needed to check to make sure my things were independent. I'm sorry to cross classes again. My simple poll. It is named after my Polish mathematician. Let's go find something we named something after. It is the Wronskian, Joseph Wronski. I got to go back and do a Wronskian. Wait a minute. Wronskian means I put this vector in the first column, and I put this one in the second column. And I take the determinant. What's that determinant? Ah, shit. In order for my solutions to be independent, the Wronskian has to be non-zero. This is not just zero, it's zero everywhere. Well, that's not very nice. I need something extra to add on, not just use te to the 2t. I need more. So what if instead of using this as a second thing, I say, I'm going to add on something else. Where P1 is a vector. So I'm saying this is the extra bit I'm going to add on. And if I'm right, then this piece will work. But it turns out that I know something nice that happens. If this is a solution, what's the derivative of this? All right, wait a minute. What's the derivative of t e to the 2t? Come on, people, you can do derivatives. Mumble, mumble, mumble. Because I need the product rule. Derivative t first, and then the derivative e to the 2t gives me the 2. And then over here I get a 2. Yes? Now, wait a second. We want x prime to be equal to a x, where A is our matrix. And in this case, that was the matrix above. Right? That was our differential equation. But A times X is A times 1 t e to the 2t plus A times P1 e to the 2t. That would be what I get if I multiply A by this whole thing. I want these to be equal. That's disgusting, isn't it? Well, wait a second. Hang on a second here. Here's my t e to the 2t part. Here's my t e to the 2t part. So this piece needs to match that piece. And this piece needs to match those pieces. Oh, wait a second. I like this because that kind of looks like my equation. I want A minus 2P1 to be equal to 1, 1. I move that to be up there. The e to the t2, e to the 2t terms, right? AP1 minus AP1 minus 2P1 should be equal to 1, 1. That's the same as A minus 2I times this vector should be equal to 1, 1. Hey. A minus 2I. Isn't that the same thing we did where we put in lambda equal 2? Way back up here, we put in 2. We got A minus 2I right here. But now instead of 0, 0 on the other side, I want to put the 1, 1 on the other side. So this new matrix is creating what is called a generalized eigenvector. We're adding something extra to the eigenvector we had before, and that's going to make it be, quote, independent. It's going to point in a different direction. Do the reduced to echelon form on this. What do I get? The top row and the bottom row should cancel each other out completely. I should get a row of zeros. What do I get on the top row? Okay, so the equation is x1 minus x2 equals negative 1/3, isn't it? Or x1 equals x2 plus 1/3. Let me write that as a vector. My bottom choice can be anything I want. X2 could be anything. That's my free variable. But my bound variable adds 1/3, doesn't it? Is. Oh, yes, it would be minus 1/3. Thank you. I don't know why I dropped the sign. My fault. -1 to me. Okay. Let me separate this. I'm going to write this as t and negative 1/3, 0. Hey, wait a second. This is 1 times t, isn't it? This is my generalized eigenvector. This is the piece I want to use instead of just a t. I need to know what this extra piece is here. So my second solution is C2 times. C2 times what? All of this. 1 plus negative 1/3, 0, e to the 2t. So you see how we still get that t e to the 2t like we wanted? But we also get something else. And that something else actually changes our phase portrait. And our phase portrait now looks like there's only one line where everything is going out. There are not two lines, there's only one. But everything around that one line is twisting because of this. Page 361. This is for a slightly different problem. This one's listed as a sink instead of a source, because here the eigenvalue is negative. It's -3. Our eigenvalue was +2. So here all the arrows are pointing in. In our picture, all the arrows should be pointing out. By the way, this can be generalized if I have more than one missing vector. I could have two missing vectors. I could have a 3x3 where I only came up with one eigenvalue. That's not just deficient, it's twice deficient. In linear, we talked about the difference between geometric multiplicity and algebraic multiplicity. An eigenvalue had algebraic multiplicity, depending on how many times it showed up in the eigenvalue equation. It had geometric multiplicity based on the number of eigenvalues it had. So in this case, an algebraic multiplicity of 2, because it was in there twice, but a geometric multiplicity of 1. And that difference is why I needed this extra bit. In addition, this is related to what we spoke of as the Jordan normal form, or the Jordan canonical form of a matrix. Back when we talked about diagonalization, which I think if you're taking linear this semester, you're getting to in like a week. There are other options for how to get this even better, but that involves actually manipulating the matrix, and I think that's beyond the scope of what I want to do. Take a look at the example on page 360 if you want to see more, where it says shows another way to get the second solution. Okay. Questions? This is nuts. But my goal is to stay linearly independent. When I have two solutions, it's just so much easier. When I have enough eigenvectors to go with everything, it's just so much easier. But there are ways around it when I don't. Just like we did with our repeated roots. I got to find a way around it. Two roots, repeated roots. What's my other option? I sure hope not. I don't want to do partial fractions. I'm just looking at quadratic. Two roots, one repeated root, or you'll notice I picked the right finger for that, didn't I? Two real, one repeated, complex roots. Ah. I have already told you of my deep and abiding love for complex numbers. This is going to hurt. I want the eigenvalues for this. Just for the record, this time I'm going to do it backwards. Instead of doing A minus lambda, I'm going to do lambda minus A. Lambda I minus A is lambda minus 5 minus 1 positive 2 lambda minus 3. The reason I did that is because now the lambdas are positive. But be careful, you have to remember to change the signs on all of the non-diagonal terms. So the determinant of lambda I minus A is lambda minus 5 times lambda minus 3 minus negative 1 times 2 lambda squared minus 8 lambda plus 15 plus 2. Wait a minute. I'm going to do completing the square. But I'm going to do it that way because it's really easy from here. That's lambda squared minus 8 lambda plus 16 plus 1. Because isn't 16 half of 8 squared? Oh, that makes my life easier. That makes this lambda minus 4 squared plus 1. When I set that equal to 0, I get lambda minus 4 squared equals negative 1. So lambda minus 4 is plus or minus I. Lambda is 4 plus or minus I. If all of the entries in my matrix are real numbers, and I get a complex conjugate pair of roots for eigenvalues, then the eigenvectors are conjugate too. Now, what that really means to me is that I only have to solve the eigenvector once. So I'm going to make my life happier. And I am going to pick one eigenvector. You want to do 4 plus I or 4 minus I? 4 plus? Here's the worst part. I'm about to break the calculator. Calculator won't do complex numbers. All right, wait a minute. Lambda minus 5. 4 plus I minus 5. Then minus 1. Then 2. And lambda minus 3. 4 plus I minus 3. 0. I got to fix this. This is minus 1 plus I minus 1, 2, 1 plus I. Mother. Okay, hang on a second. I'm gonna cheat and cheat hard here. Ready? I know 100% that the determinant of this matrix is 0. If the determinant of this matrix is 0, I should get a row of zeros. If I know I'm going to get a row of zeros, screw it, just cross out the bottom row and leave the top one. Do I have to do the work? No. I know I'm going to get a determinant of 0. This only works in the 2 by 2 case. If it's 3 by 3, I'm in deep shit. But if it's 3 by 3 and I give you this as homework, I expect you to be doing this on Wolfram Alpha. Since I must get a row of zeros, I'll just throw out the bottom row. By the way, that's an arbitrary choice. You could just as easily throw out the top row. But I promise there's a reason I threw out the bottom row. What is the equation that comes from this? Well, let's leave it like this. Or I can move that over, and I can say minus 1 plus I times x1 is equal to x2, right? So let me make my life easy and write you a vector that I know is going to work. I'm going to let x1 be 1. What's x2? Ta-da! Now, up at the top of the screen, there's a sentence that says, when I have a real matrix and it's got complex conjugate eigenvectors, then the complex conjugate eigenvalues, then the eigenvectors are conjugate too. And that means that if I do this exact same procedure with lambda equals 4 minus I, the vector I get is 1, -1 minus I. The only thing I change is the plus that's between the I changed to a minus, plus changes to a minus. That's it. But I really only need one of them. I really only need one. Because the problem is that now the right thing for me to use, is vector e to the eigenvalue. So really, the correct solution looks like this. Actually, scratch out that C1 for the moment. No, no, that's disgusting. I need to be able to insert emojis that I write by hand because right now I want to put a little barfing face next to this. Yeah. Wait a minute. When we had complex roots, what did we do? Turn them into cosines and sines. There's a way to do that here. There are formulas in the textbook that I have never in my entire life bothered to memorize. Because I'm going to do the same thing we did before. And I'm going to take the real part and the imaginary parts and separate them. I'm going to do that up here in the exponent, and I'm going to do it in the vector. So I'm actually going to write this out like this. I have e to the 4i plus it. That's e to the 4, e to the it. Because when you add powers, you multiply. Wait a minute, that should be 4t. Because the t is distributed. I gotta do it right. Can't stop. What do I do with e to the it? It's time for my buddy Euler. Cosine t plus I sine t. Notice this e to the 4t is going to hang around for a while. I'm just going to stick it out front for the moment. Now that looks like, except for the vector, that looks like what we did back in the second order case. E to the real part t, cosine, imaginary part sine, the beta is 1 here, right? The number next to the I is 1. So I get cosine 1t and sine 1t. This matches the we did before. I like that part. Here's where I start to mush things around. I'm going to multiply this into the top row and the bottom row. On top, I get cosine t plus I sine t. That's not particularly ugly. But on the bottom, I've got to multiply two complex numbers together. I'm going to multiply this cosine times the -1. I'm going to multiply the -1 by the I sine, minus I sine t. Then I'm going to multiply the I by the cosine t. And then I'm going to multiply the I by the I sine t. What's I times I? So I get minus sine t. Please notice, there are 3 parts that are real. 1 in the top row and 2 in the bottom row. There are 3 parts that are i's. 1 in the top row, 2 in the bottom row. I'm going to split this into 2 vectors. In the first vector, I'm only going to put the real parts. In the second vector, I'm only going to put the I parts. And now I'm going to strip off the I. And I've got 2 vectors with 2 pieces. There's x1, there's x2. Only thing missing, C1 and C2, right? Well, guess what? All you do is you stick a C1 on the first part and a C2 on the second part. There's your solution. Visually. Now what I get are spirals. E to the 4t. What happens as t goes off to infinity? It gets big, right? Which means these spirals go out. If it was e to the minus 4t, then the spirals would be going in, wouldn't they? And if it was e to the 0t, we'd just be going around and around and around and around, wouldn't we? Phase portraits for stuff like this go out in a spiral. If the real part is 0, we get ellipses, whose major and minor axis are the vectors that go with the cosine and the sine. So notice that in this first thing, I could write that as 1, -1 cosine t plus 0, -1 sine t. And over here, I'd write it as 1, -1 sine t and 0, 1 cosine t. These vectors point in the same direction. What about these vectors? You want to do that again? But not particularly different directions, but exactly opposite directions, which means they're on the same line. So I have 1, -1, 1, -1. That's the direction of one axis, and 0, 1. There's my ellipse spanning these two directions. Now, if you would rather write down the formulas for which piece goes with which, with the two vectors, that's here on page 364. You see the way they break them all up and do this? I lost track. But you are welcome to write these formulas down for your formula sheet. I think it's a whole lot easier just to remember Euler's formula. E to the it is cosine t plus I sine t. And then remember how to multiply complex numbers together. Does this absolutely suck? Yes. Is this more realistic? Also. Whew. So, depending on what eigenvectors we get, distinct real, repeated real, or complex, I'm going to end up with different types of results from my system. And the best part is, with constant coefficients, there was no Laplace transform needed. However, these were all homogeneous systems. So what happens when it isn't? We'll do that tomorrow. I'll see you all then.